Okay, we're now going to move on to logarithmic functions and their graphs. Now, as I mentioned before, logarithmic functions and exponential functions are very closely related. Let's talk about exponential functions here again. And so let me pause here and put a graph on. Okay, so I'm going to go ahead and graph just a generic exponential function here. And now, if we're talking about, I'll go ahead and just make this point here 1. And so we know an exponential function looks something like this, right? Okay, well, before we even talk about logarithmic functions, let's talk about some other properties here of these exponential functions. Well, one thing we should maybe comment here is that there is another way to write some of these sometimes. You'll sometimes see an exponential function as f of x equals b times a to the x. And what this b is here would be the y-intercept. You notice how in this graph we have the y-intercept of 1. And that would be because if this was like, for instance, f of x equals 2 to the x, the y-intercept is 2. The y-intercept is 1 because 2 to the 0 power is 1. But then if you look at something like, well, if you have like 3 times 2 to the x, now this is the way a lot of textbooks write it. I sometimes like to write this as 3 times 2 to the x with the parentheses there to emphasize that we have an exponential function multiplied by 3. The first thing I want to emphasize is you cannot multiply that 3 and 2 together and get 6. You just can't do that because of this exponent here. But if you see here, g at 0 would be 3 times 2 to the 0 power, which would be 3 times 1, which is just 3. So if you have something where a b here is, you just get that as the y-intercept. So that's kind of another property here of exponential functions. So maybe even instead of writing 1 there, I'll just go ahead and write b. So it's the y-intercept. Okay, now what else should we talk about exponential functions here before we talk about logarithmics? Well, notice here that the exponential function passes the horizontal line test. Well, what does it mean if it passes the horizontal line test? So let's write this down here. Exponential functions pass the horizontal line test which means they are one-to-one and have inverses. Remember when we talked about inverse functions? Well, it's coming back again here. Exponential functions will have inverse functions because they're one-to-one. All right, so that's really what a logarithm is. Logarithm is the inverse function of the exponential function. We'll write a definition down here in a second, but before we do that, I find let's just go ahead and draw another graph here. And so let's go ahead and just make this the y-intercept. And so this is my exponential function here. Now, I did a scale here just of 1 and 1 because remember, inverse functions, if you look at their graphs, we can sketch the inverse function of a to the x. It could be e to the x, but this is just, again, a to the x here. We can sketch it by just reflecting it across this line y equals x. So we can say, okay, well, you know, there's a point right here, and this is roughly halfway here. So we've swapped the x and y. So this would be 0, 1, so that's going to go to 1, 0. So there's going to be a point right here. Let's do a different color. Point right there. And then this is like, the way I have it drawn is like -2, a half maybe, something like that. And so -2 and a half would be 1/2 -2. So it'd be down here like this. Or the other way, remember, you can do it is saying, okay, if I do a line here, I'm going to do the same distance perpendicular, and that's going to put a point about right here. And then if we sketch this in here, this blue curve is the inverse function. So this is going to be a logarithm here. But let's already look at this. Because this is an inverse function, we know the domain and range. Because remember, domain and range is flip-flop. So the range of the exponential function was f at x greater than 0. So the domain here is x greater than 0. And the range is going to be the domain of a to the x. So this is from -infinity to infinity. Okay, so now that we've gotten this sketch here of the exponential function and the inverse function, we can go ahead and write a little bit more formal definition down. So, definition here. This is logarithmic function with base a. So this is going to kind of reiterate the domain we just said here. So for x greater than 0, and then a has to be greater than 0, and a is not equal to 1. So we don't have a being fractions. And remember, we can always convert any fraction of an exponential function to something bigger than 1. But so a is greater than 0. Let me start over here. I just got myself distracted here. Okay, so logarithmic function with base a. So we're going to start for x greater than 0 and a greater than 0. A not equal to 1. Now we again don't have a equaling 1, the same reason we didn't have a equaling 1 with the exponential functions. Now x is greater than 0. This again is because the domain of my logarithmic, we can look at the inverse function I just drew up here. The domain here is going to be x greater than 0 because the domain and range flip between the exponential and logarithms. So then we have that y equals the log base a of x if and only if x is equal to a to the y. So this is kind of a little odd definition here. The definition is actually using the exponential function, and what we've done is we've purposely defined this. Defined logarithms to be inverse functions of a to the x. And that's all this definition is doing here. And what I like to also do though here is really, so I mean this is our definition, and it's read, you know, log base a of x is how you read it. What I'd really like to do though is actually give a little bit more, what do logarithms tell us here? Well, the logarithm gives the exponent to put on A in order to get x. In other words, this is really what I want us to remember. Logarithms give exponents. Now, to kind of go through this, let's look at some basic examples of some logarithms here. So if we look at the log base 2 of 16. So what this problem is asking us to do here is it wants to know what is the exponent to put on the number 2 in order to get 16. So that's what the log base 2 of 16 is saying, is what exponent do I put on 2 in order to get 16? Well, this is actually just 4. 2 to the 4th power is 16. And you can just kind of do that by some guess and checking here if you wanted to, but I always think of it as like, well, 16, this would just be 2 to the 4th power. So you're saying what exponent do you put on 2 in order to get 16? Well, 16 is 2 to the 4th, so the exponent would be 4. So that's why log base 2 of 16 is 4. Now we could do another one here. Log base 6 of 36. This one should be pretty straightforward here. What exponent do you put on 6 in order to get 36? Well, this is, of course, just 2. 6 squared is 6 squared is 36. Now, you might notice on your calculators you do have a logarithm button, but not all these bases are necessarily there. Well, we will talk about how you can compute for any base. That will be in a couple videos here on how you can do that for any base. But for right now, let's talk about the two logarithms that you'll probably see on your calculator that are on most calculators. So we have just log of x, and this is what's referred to as the common log. And the common log is simply got a base of 10. So log base 10 of x is equal to the log of x. So for instance, if you do log of 1000, and if you just even type it in your calculator, you should get an answer of 3. So now, that's of course just because the base here is 10. 10 to the 3rd power is 1000. But then if we do something like log, for instance, of 50, well, if I think about this for a second, well, not log equals 50, do the log of 50. Well, if I think about this for a second, I'll put this off to the side here. I know that 10 to the 1st power is 10. 10 to the 2nd power is 100. So log of 50, the exponent should be somewhere between 1 and 2, because I'm asking myself, what is the exponent that you put on 10 in order to get 50? Well, 10 to the 1st is 10. 10 squared is 100, so it's going to be between 1 and 2. So if we plug this into our calculator, we get 1.69897, and it's got some more decimal 000. So that's the exponent we put on 10. And again, to emphasize that these logarithms are giving me exponents, let's in fact just do 10 to the 1.69897. So if we do 10 to the 1.69897, well, my calculator, when I did that, gets 49.9999, several nines, and then like a 5. Which you might say, hey, that's not 50. Well, of course, because really this answer goes on forever. This is an irrational number and it goes on forever. So I rounded it to this number, so I'm not going to get exactly 50, but clearly, I mean, that's 50 if you round it. So this is, approximately 50. All right. The other one that you probably see on your calculator is ln, and this stands for natural logarithm. And if you think about this for a second, you might guess what the base is. The natural logarithm of x is equal to the log base e of x. So again, we're asking ourselves what exponent we'd put on e. So those are the ones that most calculators are going to have. Some calculators also have a log base b button or log base a button, but I'm not going to worry about those because we have other ways we can compute the logarithm using a calculator of any base, which we'll get into later on. Alright, so let's talk, to finish up this first video here, let's talk about some of the properties here of logarithms. And to do that, let's go ahead and even sketch a graph here. So let's even just sketch the graph of log base 2 of x. All right. Oh, good enough. Oh no, my little OCD is not going to think that's good enough. Sorry about that. Okay, there we go. Okay, log base 2 of x, and we'll say this is f at x. So we're going to plot this here. So let's just go ahead and plug in some values here. So if we have log base 2 of x, and then we have x. Well, first off, I can only put in positive numbers because that's the domain of a logarithm. So my domain, remember, is x is greater than 0. And then, well, let's go ahead and do some ones here. So if x is 1, the log base 2 of x is 0. Because you're saying, what do you put on the exponent of 2? What exponent do you put on 2 in order to get 1? Well, 2 to the 0 power is 1. Then if x is 2, this would be 1. If x is 4, this would be 2. And I'm not going to be able to graph it on this graph because it's not big enough, but if x is equal to 8, the log base 2 of x would be 3. And we could do some smaller numbers too. If you did 1/2, this would be negative 1. 1/4 would be negative 2. So you can kind of see how it's really easy to get some points on these logarithms. Alright, so it's got an x-intercept of 1. And then at 2, it's 1. And then 4. And then at 1/2, it's negative 1. And then at 1/4, it's negative 2. So, not the best sketch, but you get the idea here. So let's talk about this here. Well, what are some properties of this? Well, let's first see here the log base a. So any base a of 1 is equal to 0. What that means here is that my x-intercept is always at 1. Well, what else do we have here? That the log base a of a is 1. And again, that should make sense because what's the exponent here? That exponent would be a 1. So we can further apply this to the log base a of a to the x is equal to x. And those are all kind of present in this graph here. Now let's maybe look at one more graph and the same thing here. Let's also go ahead and graph g at x equals log base 3 of x. So I'm not going to create the table here, but you could if you wanted to. So it's going to be 1 there. And then at 3, it's going to be 1. And then actually at 9 is where it's going to be 2. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would actually be, sorry, this is where that point 3 should be 1, and then so it's already in my table here, and then it will be negative 1 at a third, and then it's going to be even smaller here, so kind of get an idea here. So you can see the bigger the base, the more bent down this is going to be. Alright, now we could do more graphs of these, and you can also apply transformations on them, but we're not going to do a lot of that. Alright, so I think we'll go ahead and wrap this video up here. I'm just looking at my notes here to see if there's anything else I want to talk about. No, I don't think there is. You can still apply the same transformations, like, horizontal shifts, vertical shifts, reflections, things of that nature with logarithms. So there's not really anything else here. So actually we'll be moving on to properties of logarithms in the next section, and we'll probably, or the next video, and we'll probably have several videos dealing with properties of logarithms.